Okay, so good morning. Welcome to the class. From today on, we're going to learn the calculus and vectors MCV for you. Today is the first lesson of chapter 1. Chapter 1 is about introduction to derivatives. Today is lesson 1 of chapter 1, which is about rates of change and slope of a curve. Well, I guess most of you have already learned the slope of curve and rates of change in the last few lessons in MHF for you. So let's give it a brief recap. Okay, first of all, let's have a look at today's learning goal. After this lesson, you should be able to understand the rate of change is a measure of how quickly one quantity, the dependent variable, changes with respect to another quantity, which is called the independent variable. Then understand and interpret the concept of average rate of change. Then calculate the average rate of change from a graph, a table, or an equation of a function. Understand and interpret the concept of instantaneous rate of change and estimate the instantaneous rate of change at a specific point using approximation from a graph, a table, or equation of a function. So let's have a look at these key points one by one. Okay, first of all, the concept of average rate of change. Okay. Okay, please get prepared to take any notes you need. Okay. The average rate of change between 2 points corresponds to the slope of the secant between the points. For example, as shown in this graph here, the average rate of change of y with respect to x between 2 points P1, which is here, and P2, which is here, is determined as follows. So suppose we have a function curve highlighted in red. Then we have a point P1 here with coordinates x1, y1, and another point P2 with coordinates x2, y2. Then the average rate of change between these 2 points is defined as delta y over delta x, which is change in y divided by change in x. Quite intuitive, right? Which is y2 minus y1 over x2 minus x1. Any questions? Okay, so note here, throughout this course, if not specified, we only study the calculus of one variable functions in real number set. Okay, so this is our scope of this lesson. One variable functions and in real number set. Okay, any questions? So this is just a definition of average rate of change between 2 points. Okay, if you need more time, just let me know. Okay, otherwise we'll just go to the next slide. Any questions? No? Okay. Another representation of the average rate of change is we can actually denote the length between 2 points. The horizontal length is h. If h represents the interval between the 2 points on the x-axis, then the 2 points can be expressed in terms of a and a in terms of a, which are a and a plus h, right? So suppose we have point P, the x coordinate of P is a, then the coordinates of P is a, fa, right? And then because the distance between these 2 points is h, then we know the x coordinate of point Q here must be A plus H. You understand? This is just another expression of the average rate of change. Then we know the coordinates of Q is A plus H, F A plus H, right? Then we know the coordinates of point P and point Q. Then we can express the average rate of change between P and Q. Also using the same formula, delta Y over delta X. Then the delta Y here is the difference between the two Y coordinates, which is F A plus H minus FA. And the difference between the X coordinates is A plus H minus A, which is just H, right? Of course, H cannot be 0, otherwise Q is on top of P. Then this expression is called difference quotient. This is just another expression of the average rate of change. But in nature, they're the same, right? The average rate of change is just difference between Y over difference between X. You understand? Okay, then let's see some examples, okay, to illustrate this concept. Okay, first example, calculate and interpret average rates of change from a graph. So suppose we have a graph that represents the amount of money in a bank account over 1 year period, as shown here in this graph. So there are 3 questions you need to consider. Question A, how much money was in this account at the start of this year and at the end of this year? Okay. Question B, what does the graph tell you about the average rate of change of the amount of money in this account in the following intervals? First, month 0 to month 5. Second, month 5 to month 8. Third, month 8 to month 12. Question C, can you determine the average rate of change for the time periods in part B? Interpret these values for this situation, okay? I'll give you 5 minutes to have a look at these 3 questions. Okay, you can start now. And after that, we'll have a look at the solution together. Okay, let's have a look at the solution together. You can check if your answer is the same as mine. Okay, solution is on the right side. The first point on the graph is here, which has coordinate 0, 500. And the last point is 12, 200. So first, the initial amount of money in this account is 500, right? And the amount of that at the end of this year is 200. The second question, first, between month 0 and month 5, the graph is aligned with positive slope. The average rate of change is constant and positive. The amount of money in this account is increasing by the same amount each month. Second, between month 5 to month 8, the graph is horizontal line with 0 slope. That means the average rate of change is 0. There is no change, basically, right? The amount of money in this account does not change. Question straight, between month 8 and month 12, the graph is aligned with negative slope. The average rate of change is constant and negative. The amount of money in this account is decreasing by the same amount each month. Any questions? No? Okay. And question C, we can calculate the average rate of change as follows. First, the points that correspond to month 0 and month 5 are 0, 500, and 5, 1000, right? Then the average rate of change according to the definition, which is delta y over delta x. So delta y here is 1000 minus 500. Delta x is 5 minus 0. Therefore, the average rate of change between these 2 points is 100. And it's positive, right? Okay, the interpretation is the amount of money in this account is increasing on average by $100 per month. Okay, second, the points that corresponds to month 5 and month 8 are 5, 1000, and 8, 1000. And then according to the definition of the average rate of change, the average rate of change is defined as delta y over delta x. So in this case, delta y is 0, delta x is 3. So 0 over 3 is 0. So that means there is no change, right? No change occurs. The amount of money in this account remains the same during this period. Okay, question 3. The points that corresponds to month 8 and month 12 are 8, 1000, and 12, 200. Then the average rate of change is delta y over delta x again. So in this case, delta y is 200 minus 1000. Delta x is 12 minus 8. So that gives us minus 800 over 4, which is minus 200. So note that we just discussed the slope of this line is negative, right? So the average rate of change is negative. The amount of money in this account is decreasing on average by $200 per month. Okay, any questions? So that means you should be able to find the average rate of change given a graph like this, okay? Make sure you're able to do this. Okay, then if you have no questions, let's have a look at another example. So this time we are given a table, not a graph. So can we calculate and interpret the average rate of change from a table of values? The answer is yes. So let's have a look at this example here. A new antibacterial spray is tested on a bacteria culture. The table on the right shows the population P of the bacteria T minutes after the spray is applied. Determine the average rate of change of the number of bacteria over the entire time period shown in the table. Interpret this value for this situation. Then compare the average rate of change of the number of bacteria in the first 3 minutes and in the last 3 minutes, explain any similarities and differences there. Okay, again, I'll give you 5 minutes to have a look at this question here. All right, have you finished? Then let's check the solutions. Okay, first question. From this table, we can directly read the points are 0, 807, 37, right? Then we have 2 points. If you have 2 points, you can calculate the average rate of change between these 2 points, right? So average rate of change is delta y over delta x. So in this case, it's delta p over delta t. Delta p is the difference between the dependent variable. Delta t is difference between the independent variable. Understand? Then we can plug the numbers in. Delta p is 37 minus 800. Delta t is 7 minus 0. Then this gives us minus 109. Therefore, we can say during the entire 7 minutes, the number of bacteria decreases on average by 109 bacteria per minute, because the average rate of change is a negative number, right? So it's decreasing. The trend is decreasing. Any questions? No? Remember, we have another question to solve, okay? Okay, next question. Okay, let's have a look at the solution on the left first. From the table, the endpoints of the first interval are 0, 800, and 3, 737. Therefore, according to the definition of average rate of change, the average rate of change between these 2 points is delta p over delta t, which is 737 minus 800 over 3 minus 0, right? Which is negative 21. Therefore, we say during the first 3 minutes, the number of bacteria decreases on average by 21 bacteria per minute. Then let's check the solution on the right. That gives you the average rate of change of the last 3 minutes. So in the last 3 minutes, we have 2 endpoints, 4, 6, 5, 2, and 7, 37. Therefore, the average rate of change is again delta p over delta t, which is 37 minus 652 divided by 7 minus 4, which gives us negative 205. Therefore, we say during the last 3 minutes, the number of bacteria decreases on average by 205 bacteria per minute. Understand? Have any questions? So now let's have a look at the similarity and differences between these 2 average rate of change. So the similarity is the average rate of change in the number of bacteria are both decreasing, right? Because 2 numbers are both negative. The difference is the average rate of decrease is greater in the last 3 minutes than in the first 3 minutes. This might be because more bacteria are exposed to the spray as time passes by. Have any questions? So usually the interpretation of the result requires some background knowledge or domain knowledge. So if this is a biology problem, probably you want to know the reason behind this question with some biology knowledge, right? Okay, next one. Any questions regarding this problem? If no questions, okay, let's have a look at another example, and then we can take a short break. Okay, next example. So here you are given neither a graph or a table, right? But an expression of a function. So that means we can also calculate and interpret an average rate of change from an equation. So let's see how we can do this. Okay, this example says a football is kicked into the air such that its height h in meters after t seconds can be modeled by this function. h is a function of t, which is negative 4.9 t squared plus 14t plus 1. Okay, this actually means when t is 0, the height of the football is 1 meter, right? Question is, determine the average rate of change of the height of the ball for each time interval. First, from 0 to 0.5. Next, from 2 to 2.5. Okay, I'll give you 4 minutes to have a look at this question here. Okay, I think you should have finished now. So let's check the solution. Okay, question number 1. For this interval from 0 to 0.5. First, we need to calculate the coordinates of these 2 points, right? Here we only know the x coordinates or the t coordinates. We have to calculate the h for these 2 points. So first, we can substitute t equals 0 to find the height at 0 seconds, which means h0 is 1, right? And substitute t equals 0.5 to that equation. That gives us h 0.5 equals 6.775. That means the height of the football at time t equals 0.5 seconds is 6.775 meters. Therefore, we have the coordinates of both of the starting point and end point, right? Then according to the definition of average rate of change between these 2 points is delta H over delta T. Delta H is the 6.775 minus 1. Delta T is 0.5 minus 0. Therefore, the average rate of change of the height of the football from 0 seconds to 0.5 seconds is 11.55 meters per second. So be careful with the unit here, okay? Average rate of change measures the rate of change. So usually we'll have a unit like this. Meters per second or meters per square second or something like that. Okay, next question, the logic is the same, right? First, we need to calculate the coordinates of the endpoint and starting point. So when T is 2, H2 equals 9.4. When T is 2.5, H2.5 equals 5.375, right? Then the points that corresponds to 2 seconds and 2.5 seconds are 2, 9.4, and 2.5, 5.375. Therefore, according to the definition of average rate of change between these 2 points are delta H over delta T again, which is 5.375 minus 9.4 over 2.5 minus 2, which gives us negative 8.05. Therefore, we say the average rate of change of the height of the football from the 2 seconds to 0 to 2.5 seconds is negative 8.05 meters per second. So my recommendation is you should specify the unit here, okay? Just put the unit meters per second after the final result here. Otherwise, probably you'll miss that. Okay, any questions? Well, actually, the concept of average rate of change is pretty straightforward, right? Any questions? No? Okay, so let's take a short break, and after that, we'll have a look at the next concept, which is instantaneous rate of change. Okay, let's continue our lessons. Next, let's have a look at the instantaneous rate of change. Okay, the concept of instantaneous rate of change is given a function fx and 2 adjacent points p and q with coordinates x fx and x plus h, fx plus h, as shown in this graph. So p is here with coordinates x and fx, right? And h is the difference between the 2 x coordinates. Therefore, q has the coordinates x plus h, then f x plus h. You understand? So we know the coordinates of the 2 points. Then we can find the slope of the secant between p and q, right? This is the average rate of change between p and q, which is defined, as you can recall, delta y over delta x, which is f x plus h minus fx over x plus h minus x, right? And after simplification, this is f x plus h minus fx over h. Of course, h is not 0, right? So note here, when h approaches 0, then the ratio between delta y over delta x approaches the slope of the tangent line at p. which is here. Why is that? Because when h is very small, or when h approaches 0, can you imagine that q is actually approaching point P, right? When point Q is very close to P, very close, but not on top of P, then these 2 points is getting very, very close. Then the slope of the tangent line is actually approaching the slope of the tangent line at point P, right? Can you imagine that? Therefore, we call that instantaneous rate of change of fx at point P, or the derivative of fx at point P, denoted as the limit as h approaches 0 of fx plus h minus fx over h, or we can use the notation here, derivative of fx, which is f prime x, fx prime, or dy by dx. This is another notation of the instantaneous rate of change, or the derivative of y in terms of x with respect of x. So note here, in this concept is only applicable when such limit exists at point P. So sometimes the limit does not exist, which is not always true. We will discuss this more in our following lessons. We'll discuss this. When will this limit not exist? And when will this exist? Okay. So basically, the instantaneous rate of change is a limit when h approaches 0 of the average rate of change between point P and Q. Okay. You understand? Okay. So next, let's have a look at some examples of the instantaneous rate of change. Okay, first example, given a graph of a function, estimate the slope of the tangent line or instantaneous rate of change at a specific point using approximation. The graph on the right shows the approximate distance traveled by a parachutist in the first 5 seconds after jumping out of a helicopter. How fast was the parachutist traveling 2 seconds after jumping out of the helicopter? In other words, what is the instantaneous rate of change of distance with respect to time? Well, what is the instantaneous velocity at time t equals 2 seconds? If you are given this graph. Okay, 2 seconds is here. Well, let's mark the 2 seconds. When t equals 2, this point is here. So how do you decide the instantaneous rate of change at this point? Okay, I'll give you 5 minutes to think about this question here. Okay, let's have a look at the solution of this question. So here we note that in order to find the instantaneous rate of change, we need to find another point that is as close as possible to P, and whose coordinates is also easy to read, right? So let's have a look at the solution here. The parachute's velocity at 2 seconds corresponds to the instantaneous rate of change at t equals 2 seconds. Calculate a proximate value of the instantaneous rate of change. Let P be the point on the graph at t equals 2 seconds. Then determine the slope of a secant passing through P and another point on the curve that is very close to P. We can use this value as approximation of the instantaneous rate of change. Therefore, we need the other point is close to P and whose coordinate is easy to read, right? So we can choose the point Q, which is here. Because Q is sufficiently close to P, and coordinates of Q is also easy to read, right? X coordinate of Q is 3, and Y coordinate is just the mid value of 40 and 50, which is 45. Therefore, we can use the coordinates Q to evaluate the instantaneous rate of change. Therefore, the slope of the secant PQ is delta D over delta T, which is 45 minus 20 over 3 minus 2, which is 25, right? Using a secant, the parachute's velocity after falling for 2 seconds is approximately 25 meters per second. Okay, I'll give you 1 minute to have a look at this solution here. Okay, if you have no questions, let's have a look at the next example. So here, let's see this example. Just illustrate that given a table of values of a function, you can also estimate. So note here, estimate, not the exact value, okay? We can also estimate the slope of the tangent line or instantaneous rate of change at a specific point using approximation. Okay, so note here, if you are not using the concept of limit, you are only evaluate the instantaneous rate of change approximately, okay? No matter how short your interval is, your value toward instantaneous rate of change is only approximate value, not exact value. If you want to find the exact value, you should introduce the concept of limit, okay? We'll talk about the concept of limit in our next lesson. So here, let's only focus on the concept of instantaneous rate of change using approximation, okay? So here in the table at right, the distance of the parachute is in the previous example is recorded at 0.5 seconds intervals. question is how we can estimate the parachute's instantaneous rate velocity at 2 seconds. Can you give a approximate value of the instantaneous velocity at 2 seconds? Okay, I'll give you 3 minutes to think about this question here. Okay, have finished. Yes, let's check the solutions. You can compare the solution with your result. Okay, so to estimate the instantaneous rate of change from a table, you can calculate the average rate of change over a very short interval by using points in the table that are closest to the tangent point. Because the table here shows that at 2 seconds, the parachutist has traveled a distance of 20 meters, right? Therefore, a point that is close to 220 is either the point here or the point here, right? So note here, these 2 points, both of these 2 points has distances with the point 0.0 of 0.5, right? So whether it's before this point or after this point, but interval all are both 0.5. So we can choose either one. So for example, let's choose this point here to calculate the approximation of the instantaneous rate of change. Then the average rate of change between these 2 points is delta D over delta T. Delta D is 31.2, 31.25 minus 20 over 2.5 minus 2, right? And the result is 22.5. So we can use this value. So note here, this value is only a average rate of change between these 2 points, right? But because these 2 points are very close to each other, so we can use this value as approximation of the instantaneous rate of change or instantaneous velocity at this point, 2.0. Then we can conclude that the parachutist velocity at 2 seconds is approximately 22.5 meters per second. You understand? So note here, we can also choose a point 1.5, 11.25 here. You can choose either point. Any questions? Okay, have a look at this solution here. Any questions, just let me know, okay? All right, if you don't have any questions, let's see the next example, which is the last example of today's lesson. Okay, so this example illustrates that given an expression of a function, we can also estimate the slope of the tangent line, also known as instantaneous rate of change at a specific point using approximation. Okay, here, let's have a look at the example here. The flower pot falls freely from 98 meters above the ground. The height in meters denoted by S of the flower pot in terms of the elapsed time in seconds from the moment it falls denoted by T can be modeled by the function S equals 98 minus 4.9 T squared, where T is between 0 and 2 times square root of 5 inclusive. Estimate the instantaneous rate of change of the flower pot's hat at T equals 2 seconds. Okay, I'll give you 5 minutes to think about this question here. All right, let's have a look at the solution here. So note that the definition of the slope of the tangent line is defined by a limit, right? A limit of the difference between y-axis and x-axis, which is fx plus h minus fx over h. H is the difference between the 2 points. The limit as h approaches 0 of this function is actually the instantaneous rate of change at point P, right? So following this definition, we can evaluate the instantaneous rate of change at t equals 2 seconds. Okay, so according to the definition of instantaneous rate of change, the instantaneous rate of change of the flower pulse height at any point t is given by st prime. So this is instantaneous rate of change at any time t, right? This is by definition the limit of st plus h minus st divided by h as h approaches 0, right? Then we can insert t plus h to the expression of s. So that gives us 98 minus 4.9 times t plus h squared minus st. St is 98 minus 4.9 st squared. Then we can expand and simplify the numerator, which gives us negative limit as h approaches 0 of negative 4.9 times t squared plus 2ht plus h squared, then plus 4.9 t squared over h, right? Then the numerator can be simplified to negative 9.8 th minus 4.8 h squared over h, right? So note here, this is a limit as h approaches 0. H approaches 0 means h is not 0, but a number that is very close to 0, right? Therefore, we can cancel the h in the numerator and denominator position. So we can cancel h here, here, and here, right? So this expression becomes the limit of negative 9.8 t minus 4.9 h as h approaches 0, right? So as h approaches 0, the limit of this function is which value? You need to consider that question. So far, we haven't learned anything about the limit, right? We'll introduce the concept of limit in our next lesson. Therefore, so far, we can let h be a very small number. So, for example, we can let h be 10 to the power of negative 10. This is a very small number, right? Because so far we haven't known how to solve a limit of a function. So you can just let h be a very small number to approximate the effect of h approaches 0. So for example, if h is 10 to the power of negative 10, then we can say the instantaneous rate of change or instantaneous velocity at any time t, st prime, is approximately negative 9.8 t minus 4.9 times your h here, right? Which is 10 to the power of negative 10, which is approximately the former part, because when this number is very small, the later part will be very small. The effect of the later part can be ignored. Therefore, it's approximately negative 9.8 t, right? This means at any time t, the state instantaneous rate of change at any time t is just negative 9.8 t. Therefore, we say at t equals 2 seconds, you can just plug this value into that equation here. So we use this notation. At time t equals 2 seconds, the instantaneous rate of change, st prime, at t equals 2 is approximately negative 9.8 times 2. which is approximately negative 19.6 meters per second. Therefore, we can make the conclusion at t equals 2 seconds, the instantaneous rate of change of the flower pot height is approximately negative 19.6 meters per second. Any questions? Okay, so if no questions, this is the end of today's lesson. So finally, let's make a quick recap of today's learning goals. So after this lesson, now you should be able to understand that a rate of change is a measure of how quickly one quantity, that is a dependent variable, changes with respect to another quantity, which is the independent variable. Then understand and interpret the concept of average rate of change. Then calculate the average rate of change from a graph, a table, or an equation of a function. Then we have discussed the instantaneous rate of change, right? You should also be able to understand and interpret the concept of instantaneous rate of change. And estimate the instantaneous rate of change at a specific point using approximation from a graph, a table, or an equation of a function. Okay, so if you don't have any questions, please download today's homework and try to complete that and submit that before the deadline, okay?